Hello again. This lecture we will be addressing scientific notation and significant figures. Scientific notations are used to express either very large numbers or very small numbers in a practical way. For example, the sun diameter is such a large number, and if you are to express it in a regular or traditional way, there are too many digits and chances are we can miss, add, or subtract a digit or two if we try just to write it in a traditional way. So a more practical way is to express it in scientific notation. So you can say 1.392 times 10 to the power 9 meter. Same thing when we express a very small measurement like the average diameter of an atom. It's such a small number, so writing it the way it is will also allow us to be susceptible of making mistakes. It will be a much more practical way to say 3 times 10 to the negative 10. So when we have a large number, the exponent is a positive value. When we have a small number, the exponent is a negative value. So to write things in scientific notation, here are the parts. We have what we call the 1.23, which is the coefficient, and the coefficient is a number between 1 and 10. Then we have the exponent part, which is the exponent is an integer and it can be either positive or negative, and it's always a whole number. Now, writing numbers to reflect precision means that we have to keep the accurate number of significant figures in any measurement. Please note that I just said measurement. So significant figures are only going to be present when we have a measurement. So significant figures in a definition is listing all the digits that we are sure of and the first one we estimate. That's why I said it has to be a measurement, because we only estimate digit when we are measuring or using a measuring tool. So here is a measurement, 45.872. If that is the actual number of significant figures, the way it looks to me that the person who did measure is 100% sure that it is in the 40s. It is actually 45. It is indeed 45.8. We also know it is 45.87, and then we could not really have a graduation to confirm the 2, so we estimated it to be 2. So there are 5 significant figures in this measurement. All of them are certain, and the last one, which is part of 1,000, is estimated. Now, if a student measured a length of an object and reported 12.3 centimeter, then the student is reporting 3 sig fig. What does that mean to you? It means the student was 100% sure of the 12 and estimated the 0.3. And because the 0.3 is estimated, it means the measurement, the actual thing, can be anywhere between 12.2 to 12.4. If another student used a different measuring tool, the number of sig fig will be different depending on the tool, and recorded 12.30 centimeter, then this student did report 4 significant figures. And since the last digit is where the estimation is, it means that the real value is between 12.29 to 12.31 centimeter. So let's write number to reflect precisions. Every measurement has uncertainty. We already know that. Here is an example. This is a nail, and if I am asking you to look and report what you see, what is the length of the nail reported to the correct number of sig fig? you have to report what you are sure of, and you have to estimate one digit. So what you are sure of, that it is a 5 centimeter. It's definitely not a 4, and it's definitely not a 6. It is indeed 5. So I'm gonna report 5. Can I see further? The answer is yes. I can see that it is even beyond 5.5, but not 6 yet. So I might estimate this to be 5.7. Now notice that I wasn't certain it's 7. I estimated it. So this is where I stop. I can no longer proceed with this. I am done estimating. So my measurement in this case, using this specific rule, is 2 significant figures. I can't do more than that. Now let me show you something. What if I have something different when it comes to my ruler? I'm going to assume right now that I have used a different ruler, and this is how the ruler is looking like. It does have extra graduation. So now let's look at what you would have recorded. You're still 100% sure it is 5, which means that it is not 4 and not 6. So you will report 5. Now, can you see further? Yes, it is not 5.5, not 5.6. It is a little bit 5.7. I can see the 7. That is part of the graduation. And is it right on it, or it's a little bit to the right? I mean, it's hard to tell, so I have to estimate. Maybe it's 5.71. So now when I changed the tool, I was 100% sure of the 5. I was 100% sure of the 0.7, but I am estimating the 0.01. So therefore right now this tool allows me to report with 3 sig fig. This is a more accurate and more precise tool, clearly. Now let's look at significant figures rule. All non-zero digits are significant. So any digit that doesn't have any measurement that doesn't have zeros in it, all the digits are significant. So this measurement has 4 sig fig. Zeros at the beginning, which are like placeholders before the first non-zero digits, are not significant. So 0.08 liter, those zeros that you see them underlined, those are just placeholders, and therefore they are not significant. I did not read that, and therefore I have 1 significant figure in this measurement. Zeros in the middle, or what we call them zeros between the non-zeros, are definitely significant. So the 606 meter does have 3 significant figures in it. Zeros at the end, it depends. So without a decimal point, they are uncertain, and therefore they can be ambiguous. So the rule in this class, if I don't put any decimal points for you, I want you to consider these zeros as placeholders and therefore not significance. So this measurement here can be ambiguous. So for example, let me show you something. If I kept it as it is, as 4,500, and I didn't put any decimal point, I want you to consider that to be 2 sig fig. Now if I wrote 4500 decimal point, then these 2 digits now become significant, and therefore this measurement will have 4 sig fig total. Sometimes in certain books, I just want you to be aware of that, they will put a dash above the last significant digit, and in this case, if that's the case here, what they are trying to tell you that this 0 here was significant but this one was not, and in this case it will be 3 sig fig. Now, after a decimal, any digit is significant. So 2.0, that 0 is definitely significant after a decimal point, and therefore you have 2 sig fig. And putting everything together, if you look at this measurement, all the beginning of the number zeros are not significant, but all the digits after that are significant. So this 4 here is significant, the 0 here, because it is after a decimal point, is significant, the 2 is significant, and this 0 is significant. So therefore there are 4 sig fig in this measurement. Now, all digits are significant except zeros at the beginning, 0 at the end without a decimal point. There is something also that we call exact number, and exact numbers from definition are things that we know for sure that they are exact and they will not be estimated. And because they cannot be estimated, they have infinite number of significant figures. So what can we be sure of that cannot be estimated? 2 things. The first category, anything that you can count. If you count that you have 5 books, then you do have 5 books. It's not like there is a chance you can have 4 or 6. You can count them. So anything you can count is exact, and because it's exact, it has infinite number of significant figures. Another thing that is also exact if it was defined, and by that I did define, for example, that a kilo of anything is 1,000 of that thing. It cannot be 1001 and it cannot be 999. It is defined 1,000, and therefore that is considered to be exact number with infinite number of sig fig. Let's look at the following. How many sig fig are in each of the following? 24 milliliter. These are 2 sig fig, you're right, because they are all non-zero. How about 3001 gram? All the zeros between non-zeros are significant, and therefore we have 4 sig fig. 0.0320 cubic meter. Remember, the beginning at the zeros at the beginning, those are not significant, but after a decimal they are, so we have 3 sig fig. 6.4 times 10 to the power 4 molecules. Anything in a scientific notation, the coefficient, everything in the coefficient is significant, and therefore I have 2 sig fig. 560 kilogram, that is ambiguous. If I don't have a decimal point, it's 2. If I have a decimal point, it's 3. 5 pennies. Think about that for a second. How many sig fig? Do you think it's 1? No. It cannot be, because you can count the penny, and because it is exact, then it does have infinite number of sig fig. Let's see how we can perform calculations using measurements with sig fig. If you are adding or subtracting, then the same number of decimal places are the one with the fewest. So for addition and subtraction, all what matters are number of decimal digits. That's all you need to care about. So let's look at this example right here. This number here has 3 decimal places, while this one here has 1 decimal places. This is what your calculator will give you. Your calculator does not understand that you are following sig fig. If you are to report that, you can only report 1 decimal place. So the way to report it will be 90.4. Now let's look at this subtraction. Again, the first number has 2 decimal places. The second number has 4 decimal places. Your calculator will give you 0.7867. All you care about is is the decimal places. That's all you care about. The first number has 2 decimal places. The second number has 4. Therefore, your answer has to have 2 decimal places. Please note that I don't care about total number of sig fig. I'm not following number of sig fig. I'm only following the number of decimal places when I subtract and when I add. Now for multiplication and division, the rule is different. And now I don't look at decimal places, I look at total number of sig fig. It has to be the same sig fig as the fewest. Here is an example. You're multiplying 2 numbers. The first one has a 3 sig fig, the second one has 5 sig fig. The answer cannot have more than the lowest. So your answer should not have more than 3 sig fig. The calculator will give you a number with 8 digits in this case, but you have to report 3 sig fig. So what you're going to do, you're going to report 16.5. In the next division example, you have 2 sig fig divided by 5 sig fig. Your answer should not have more than 2 sig fig. So when you're going to round, you're going to end up reporting 0.061. You're going to have to round that 0 into 1 because 6 is larger than 5. If the calculation has several steps, and this is very important and you will run into examples like that, then you need to perform one step at a time and every step you follow its rules. Meaning, I have 3.489 times 5.67 minus 2.3. Notice that you have parentheses. What's in between the parentheses is subtraction. So you need to perform the subtraction and follow the rules of the subtraction. Then multiply by 3.489 and follow the rules of multiplication. Okay, so let's look at this for a second here. Let's go and perform this math together. So now the subtraction, okay, if you take these numbers to your calculator, 5.67 minus 2.3, and you want to report 1 decimal place, then you're gonna have to report 3.4. Now 3.4, you're gonna have to multiply that by 3.489, and that will give you a number with many digits in your calculator. However, you have to keep it at 2 sig fig. The calculator will tell you 11.75793. You only are allowed to keep 2 sig fig because this process gave you 2 sig fig when you followed the rules. So therefore, you're going to have to report the 10, and this 1 has to be rounded to 2, so the answer will be 12. Okay. Now let's look at the next example and see what are we going to learn in this. What if I ask you to calculate the average of the following 3 measurements? Then this is what you're going to do. You're going to add them up and divide by the total number of measurements. Now, if you do the addition, which you should do first, right? So this is the addition. You have to keep 2 decimal places. So if you are adding 2.64 plus 2.68 plus 2.70, and you're gonna have 8.02. I kept 2 decimal places divided by 3. Now some of you will say, okay, now it's division, I have to keep the smallest number of sig fig. 8.02 does have 3 sig fig, but a 3, is it 1? The answer is no, it's not 1. 3 is the number of measurements. Can you count the number of measurements? You have 1 measurement, 2 measurements, 3 measurements. This is exact. And because it's exact, it's an infinite number of sig fig. So now when you divide, you have to report the 3 sig fig, which is 2.67. 7. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2.67. 2 Okay, that will end this lecture, and I will see you in the next one.